So, in this lesson, we will continue to take a look at Unit 2, Chapter 7, Quadratic Functions. And in particular, we will look at 7.1, where we are exploring quadratic functions in the standard form. We want to make sure that you understand what is meant by the standard form and begin to get a sense of what the graph does and how it behaves in relationship to this function. The vocabulary for this section is exactly the same as it was for 7.6. We're still looking at the vertex, the axis of symmetry, maximum, minimum, domain, and range. So if you copy down those definitions in our first lesson, you will be fine as we work our way through this one. So the big question is, what is the standard form of a quadratic function? Well, to begin with, I want to remind you of a question that we did in the last lesson where I gave you an equation in the vertex form and I asked you to graph it. We went through the equation and realized that the number 1 over 3 would make our graph slightly wider, that the plus 3 would move it to the left 3, and the minus 1 would move it down 1. So we drew a graph. Mine is a little bit wonky looking, but nevertheless, it is a quadratic. All right, well, let's take that very same equation. And what I'd like to do is show you how I can take this form and turn it into the standard form. Basically, what I'm going to do is simply multiply it out completely and simplify it. So when I look at it, first of all, I'm going to get rid of the fraction. And I'll do that by multiplying everybody by a 3. And when I do, it becomes 3y. This guy right here, the 3's cancel. So all I have left is x plus 3 squared. And to save myself a little bit of time, I wrote x plus 3 times x plus 3, and then minus 3 times 1. Next, I'm going to take a look at what's inside with these two small algebraic expressions and expand them. X times x is x squared. X times 3 is 3x. 3 times x is 3x. And 3 times 3 is 9. Okay, now I'm going to take what I have and clean it up. 3x plus 3x here in the center is equal to 6x. And 9 minus 3 is equal to 6. I'm almost finished. I have y isolated. I just need to isolate y. So I'm going to divide everybody by 3. And when I do, this becomes 1 over 3x squared. This one becomes 2x. And this one becomes 2. What I have done here in expanding everything and then cleaning it up is what we call the standard form. Some people say that the standard form is where we take all of our ducks and we put them in a row. We want everything to be in descending order. So here is the general form of the standard form. You have ax squared, the x squared term comes first, the x comes second, and the number that sits by itself stands at the end. All of the ducks in a row. So we took our equation, which was in the vertex form, we expanded it and we simplified it, and we turned it into a quadratic function or quadratic equation in the standard form. Now, what we want to do is take a look at what the graph looks like. And remember, we've drawn it already. So we have a picture of it. And what we want to do is check to see if we notice anything about the numbers that are appearing in this standard form. So here's a picture of the graph. Just take a moment or two and look at that. See if you notice any similarities and pause the video. Ask yourself, okay, do any of the numbers have significance? First of all, I want you to focus on the number 1 over 3. And I want you to look back at the original, the vertex form. Hopefully you notice that the 1 over 3 is also in the vertex form. And you will recall that that tells us that the graph opens up, and in this case, that it is wider. So the term that we call a shows us when the function is reflected in the x-axis, when it is vertically stretched or when it becomes skinny, and when it is vertically compressed or when it becomes wider. Next one I want you to focus on is the number at the end, the 2. If you look at your graph, hopefully you begin to see that, hey, the y-intercept is 2. And sure enough, that is exactly the relationship. The number that sits on the end of the standard form, the c, is the y-intercept. And actually that makes sense algebraically as well, because the y-intercept is when x is equal to 0. And if I put a 0 here and a 0 there, these terms essentially disappear. So the y-intercept is c. Now, the only one left is the term we call b, and this one is a little strange. It's a little bit hard to see it, so we've actually tried something else with some other examples. And what I did was I graphed on Desmos. Here's your ordinary red y is equal to x squared. If I add a 4x, look at what happened to it. It moved to the left and down. And then when I subtracted a 4x, it moved to the right and down. So we may not be able to tell exactly what's happening because it seems to be a little bit of a fluctuation, but we can see that the b term affects the vertex, and it seems to move it in the opposite direction that we would expect. Okay, so let's take a look now in order to prepare you for some of the questions you're going to see in your lesson. Let's take a look at how the curve of a quadratic function behaves so that you might be able to give a good estimate of what the a values might be in your functions. So we're going to go into this particular drawing, and I'm going to slip into the drawing function so that I can point out a few things to you. So we know that the ordinary graph sits at 0, 0. And in fact, let me just get something that I can actually put the dot on. So we know it sits at 0, 0, which is right here. Now, take a look at what happens when I go over 1, my graph goes up 1. So it's over 1 and it's up 1. When I go over 2, it goes up 4. And maybe I'll change the thickness of that one so it's a little bit more normal. When I go over 2, it goes up 4. That is the ordinary function and how it behaves. So that is when the a value is a 1. Now let's take a look at some examples. If we take a look at this one, we're being asked to give possible values for a and c. C, of course, is the y-intercept. We take a look. The y-intercept is -4. We're all set. Now, in terms of the a, if we double check and look to see what happens when we actually move over 1, we realize if we go over 1 and up 1, we're right here. This one seemed to behave in the same way. If I go over 2, it goes up 4. So it's looking like my a is equal to 1. And of course, it's positive because this graph is opening up. Let's take a look at the next one. Now I can see that the y-intercept is 2. And so let me double check my a values as well. I can tell that my a value is probably a negative because it's pointing down. When I go over 1, it went down 1. When I went over 2, it went down 4. So this one is a is equal to -1. Next one. In this one, we see that our y-intercept is a 1. And then if we try to take a look at our value for a, if I go over 1, this time it went up 3. If I go over 2, it went up. And in fact, it goes way up here. It's up here somewhere. It seems like it went up 12, actually. And if we consider what's happening, usually it goes over 1 and up 1. This one went over 1 and up 3. My graph is skinnier. My a value then is 3. Last one, we can see our y value. The y-intercept is 2. So we can see that it's actually moved up 2. Let's take a look at what's happening. If I go over 1, it only went 1/2. If I go over 2, it only went to 2. I can see that it's shaped downward, so my a value is -1/2. Okay, there you have it. That is exploring the quadratic function when it's written in the standard form. You do have some homework that I want you to try to practice some of the ideas you've seen, and make sure you bring your questions to class.